Hello everyone. Today we will be going over the concept in data systems called reliability and overall just reliability in software systems. So inside of the world, within the concept of reliability, reliability is the backbone of user trust and functionality in the digital world. At its core, software reliably revolves around the system's ability to function under extreme conditions, handle errors gracefully, and maintain performance standards without unauthorized access and misuse. Now, faults and failures are the yin and yang of system reliability. Faults are deviations in components from their speculations or specifications, while failures are the unfortunate occasions when the system as a whole stops serving its purpose. Fault tolerance is our safeguard against these. It's our digital immune system, designed not to prevent every possible mishap that would be impractical, but to keep the system running despite them. The principle is to design systems so robust that faults don't escalate to failures. Now, a good vivid example is actually now part of the Amazon Web Service logo in of itself. This is actually known as Netflix's Chaos Monkey, which is a popular open source reliability system. And you can also Google it as well, just to be able to find different packages about it. It's basically used as a vaccine for the system. Scene for data systems, where it's able to do a check and balance type of methodology to be able to check for different faults within a given database system that would be either exploited and also provide a further backbone for systems resilience. In of itself, it is a counterintuitive method of breaking things on purpose to make them stronger. So, in particular, if we can just give one example, say for instance that it could give a brute force approach for either a hardware failure or a software type of failure. In of itself, the Netflix Chaos Monkey will try to see faults within a system to be able to try to make them robust over time. So, as we move forward in just storage systems, initially from just relying on storage systems to cloud-based solutions. So as we scale up and move to the cloud, there are going to be an increase of number of machines. We therefore also increase our potential for hardware failure since we already have more servers that are basically serving more users in itself. And so what needs to happen is that there needs to be a redundancy in the traditional process of having backups ready to step in. However, as we have new paradigm shifts between new forms of computing, we need to figure out exactly how to tolerate the loss of an entire machine with software fault tolerance strategies, allowing for things such as rolling upgrades without downtime. But there's also more reliability than just handling hardware issues. Software errors and human errors are equally potential threats. So overall, for our errors, we would typically have hardware, software, and human. Hardware typically means systems shut down. Software can refer to a bug. Then human can refer to triggering a system by either hardware or software faults. So software errors, if we want to be able to go over them in particular, software errors often stem from systemic bugs lurking just within the shadows and waiting for the right combination of conditions to occur. And to be able to combat this, there's a whole isolated testing process. To be able to help mitigate and actually test for those robust errors and try to create robust solutions as a result. And overall, with human errors, if we want to go over them, there could be a series of heuristics and misconfigurations that may in of itself override a system without us even knowing. And so what we need to do is that we create sandbox environments for safe experimentation. where in of itself we can actually understand between the human conditions and enable quick recovery and have clear monitoring for every possible warning sign. Overall, reliability isn't just for mission critical applications, it's just for general expectation when you ever have a data intensive type of system. So, if we want to go over a concept example that we're going to go over the case of a power grid outage scenario. So, now let's just imagine that we have a power grid management software. It is designed to handle the complex interplay of electricity supply and demand across the vast network. Suddenly, one stormy night, a lightning strike causes a critical server to fail. This is a fault, a deviation from the server's specification to be operational because we have lightning. That's bad. Now, if the software managing the grid is fault tolerant, the system immediately switches to a backup server without interrupting the power supply. No failure occurs in the overall power grid system despite the fault in one of the components, and everyone goes home happy. To further strengthen the system, the power company regularly conducts failure drills. Putting in here. Put a different color. Similar to Netflix's Chaos Monkey approach, they simulate server failures to ensure that the switch over to backups is seamless and the fault tolerant mechanisms are always ready. Another key aspect is dealing with software errors. So let's just go over exactly. So we have hardware. I'm just going to use a different color. 1 second. There we go. So hardware. We'll just put in Netflix Chaos Monkey. Monkey for backup. Transition. As in, there are loads of simulations already set up in place where if hardware fails, it already knows exactly where to go. It's been tested multiple times. Now, for the software aspect, let's just say that there's a bug overall and it controls the power distribution. It assumes that energy demand is constant, which is not the case because it can, since we're dealing with an electricity system, demand is going to be sporadic depending on exactly where it's being allocated. And during peak usage, the assumption leads to overloading and failures in the network. And this is a systemic software error. To prevent such a scenario, the company implements a rigorous testing and real-time protocol. So, testing and real-time protocol. There we go. In order to actually isolate those scenarios and then implement rigorous testing and real-time monitoring to detect and rectify such flawed assumptions before they cause real issues. Lastly, we're going to tackle human error. Where operators in the control center might incorrectly configure the system during maintenance, causing an outage. To prevent this, the system is designed with intuitive interfaces, which has robust testing environments that allows for a quick recovery for the missteps, minimizing the impact of human errors. So, intuitive systems. With robust testing. Easy use. So yes, overall we conduct failure drills between the hardware, software, and human errors in itself to think holistically over the impending cases of faults and failures in of itself and how do we mitigate them for the whole data system. So let me just zoom out for a second so you can get the whole picture. There we go. All right. Just write this here. There we go. hardware, software, human error. Now, let's look at a practice example to be able to cement our following concept. So, say for instance that we're working with a stock trading app. So, if we want to build a reliable system, there are a number of steps that we have to take in order to actually be able to build out the system. And as you notice, I already have a series of different components I'll be breaking down throughout the rest of the entire time. So, going back from a previous lesson, in order to actually have a data system in of itself, the data system must have a database, and it could be any kind that we want. It could be a cloud-based one, such as it could be Firebase, MongoDB, Azure, Amazon Web Services, just to name a few. And but then what we need to do, just within our following database, is that we also need to connect with cache and also queue to keep up with updates of the data in of itself. So the first step that we really need, once we have all three of these components, is that first we got to understand. I'll use a different color. One, we got to figure out the data flow. Two, design for reliability. Third, being handling failures. So, if we were to have a cache system, a popular one is typically Hazelcast to be able to update real-time data as there are new trades already going in and out, because the trades in of itself would represent parts of the queue in of itself of different time sequences that we would have. For instance, whenever we lock a trade, buy a stock, sell a stock, for instance, we would use, we can use Apache, so Apache's Kafka, actually, that's the name of it. Which we use as a queue to be able to handle the flow of trade orders that we would make for buying, selling, and or shorting, or options or futures, namely, while Hazelcast would actually be representing for the caches in real-time systems. Now, in order for us to be able to actually communicate between the data flow and understanding between high-performance trades and understanding just the whole user actions that we would have based on our three components for the data system, when designing for reliability, each of the components must be identified, and we must integrate fault tolerance for each of the components. For the database, we implement redundancy, perhaps with a master-slave configuration as one dynamic. So if the master fails, a slave can take over without the loss of the service. The cache system would be distributed across multiple nodes to handle a node failure. And for the message queue, we ensure that it's robust against message loss or duplication, even during faults, by using transaction logs and replication. And meanwhile, for handling failures, what we would have is that we plan to handle failures all across the whole system. And if a component goes down, whether in hardware, software, or human error, we're able to reroute the task to implement healthy components, and then we also make sure that we isolate those tests so that way those tests would actually be robust enough to be able to handle out different scenarios if a system goes down. If the primary database fails, the system should fail over to a replica with minimal downtime. A mechanism to retry or compensate for failed operations must be in place for the messaging queue as well, and also for our cache at the same time. So then what we need to do is that we need to implement recovery protocols as well. where that way we train on hardware, software, and human errors. So that way we implement recovery in the case of a fault. The system needs to recover gracefully. And if the database server, for instance, crashes, it should automatically restart and recover from the logs. If a cache node fails, other nodes should be able to take over the load while it's being restored. And also we implement recovery protocols for queues as well if there is some type of system backlog, or maybe there might be some type of error we don't know of. And finally, what we need to do is that we need to implement a design workflow, hence what is right over here. So 5, implement design workflow. So these 5 steps, we have to understand the data flow, then design for reliability, so that we know the faults, and handling failures, knowing what to do. Then we implement the recovery phase, and then we implement the design workflow, which is right over here, namely. So let me just zoom out of this to be able to help give the bigger picture that we have. So yes, this will be just how we go through a basic practice scenario for these 5 different steps, and also going back from our previous lesson as well, knowing that, oh hey, to create a database system, we need we need a database, we need caches, and we also need queues as well to be able to build out just different components that we already can build our data intensive applications. But then we also need in the case of reliability, we have to implement these series of steps to be able to know exactly what to do. And let's put this Apache Kafka. Sorry about that. Yeah, so Hazelcast is the cache, Apache Kafka is the queue, databasing can be whatever, and then we go through the series of 5 steps to be able to know exactly how our data is going to be flowing, and also putting out different series of edge cases and faults needed. Now, for our second practice problem, let's focus on a multiplayer game and focusing on the data flow for an online multiplayer game. For our second practice example, we're designing a data flow for new features in an online multiplayer game, a player-to-player item, first-person shooter game. This requires a series of managing different series of states between player interaction and ensuring that the virtual economy in of itself remains intact. So the first thing that we are going to need to do, well, first off, we have to know exactly what a whole database is consisted of. So a data system is consisted of a database, cache, and queue. So having those 3 components, will be able to create our data system. But then the way how our data flow is actually going to be done, we're going to go back on our 5 steps that we built from previously. Okay. Yeah. And so what we need to do is that we can use, for instance, in understanding our data flow and understanding how the database, cache, and queue are actually going to be coinciding with each other. And then I also have a handy visual over here to be able to help solidify it. Let me see if I can magnetize this for you folks. There we go. So you have your clients that authenticate, they go to different services, and they can go throughout different matchmaking. There's a fleet of them all together. It interacts with the API, and then gets to the database. Over here, there we go. So our five steps that we need in order to actually be able to create our to understand more about the reliability of our given multiplayer online playing system is that the first step we have to identify data flow, understanding, or I'm just going to put down understand the data flow. Understand the data flow. How it's all going to interact. We can use different components between different databases that are on the market, caches and queues, to be able to build up our whole data flow. And then we would facilitate different actions that players would use in a team first-person shooting environment, for instance, for a video game right here. And then the second step that we would need is to design for reliability. So and third is that we need to ensure consistency and handle failures. And implement recovery failures, implement recovery protocol, and then design / visualize the workflow. And when we are implementing recovery protocols, we always focus on the hardware, software, and human side. So if we are going to be going every single part of our steps that we have for online multiplayer function that we have for our flow, is that we need to understand the data flow and identify what data is required to facilitate different actions for users. And then for step 2, when we are designed for reliability, we would handle in of itself the different actions that we would have. So we would understand between the interactions between the database, caches, and queues over how they would manage different states for taking off different actions that players would have. And they would handle failures in the case of whenever there must be another error that has already occurred, or different heuristics that we would see for systems to be able to roll back on hardware failures, or be able to isolate and test different software components for bugs, and then also for human interaction, implement our sandbox method as well. And then finally, for our implementing our recovery protocol, once we have handled the failures and identify, we would look from the hardware, software, and human side of how we would implement them to be able to isolate and test, and therefore be able to put them out inside of our data system. And finally, we will design and visualize the workflow over how our whole system would coincide and interact between the multiplayer environment and handling such failures. So a multiplayer game architecture, implement handling failures. So let me just zoom out of this to give you a bigger picture. There we go. Okay. So we have our 5 different steps for our second practice 1. We understand the 3 different components for a data system. where it encompasses a database, cache, and queue. We can use what is already available to handle different various series of events. And then we have our 5 different steps that we use, solely focusing on reliability. Understand the data flow, design for reliability, handle failures, implement recovery protocol for hardware, software, and human interactions, and finally we design and visualize a workflow that we have over here to handle such failures. And so yes, this was system design, building data intensive applications, lesson number 2, focusing on reliability. Thank you again for taking time to watch this. If you found this playlist helpful, and you also found this video helpful, be sure to like and subscribe. And if you have any other questions, feel free to put them in the comments section. And as always, take care. Cheers. Bye-bye.